You on? Hi, everybody. I think we'll get started. There will probably be some people who are late arriving. I'm really excited about today's engineering seminar. Most of you know Jimmy Blanchette is our Director of Quality. And I remember when I was interviewing Jimmy and kind of going through his resume, he has all these really impressive qualifications. He's a master black belt in Lean and Six Sigma. But what really caught my eye was that he had designed and built a system that he's going to talk about today for communicating by bouncing radio waves off the moon. So I thought that was sufficiently cool that he should most definitely work for us. And I'm delighted to introduce him. Thank you for taking the time, Jimmy, to tell us all about it.
Thank you very much. Thanks everybody for being here. Let me turn on the microphone here. Okay, can you hear me well? Very good. So enjoy the pizza, and have a good time. So today I'm going to put the agenda here briefly. Here we go. So we're going to, first portion of the presentation, we'll go through today's challenge, the core thing that we want to achieve today. We'll explain in detail a little bit, the Moonbounce, how it works, the history of it, and also the experiments that we are conducting, which is a bit special, because we involve also an in-touch audio-video devices. So we'll explain this. We'll go through the hardware, software that's utilized, and then we're going to do actually a live demo. I do have a Moonbounce friend in the Netherlands, Europe, who volunteered for this demonstration. So we are going to take about 30 minutes for the presentation, and then we'll cut it short if we want to have enough time for the Moonbounce demo. And then we'll go live. We will use Log Me In to log into my radio station at home. And we will control the whole station, that is antenna moving around, and the radio, the fire, everything. Everything is kind of preset, as we said everything before I had this morning. We shouldn't have to do too much tuning, but we will be controlling that station and broadcasting live the two-way communication with Yo, is the name of the gentleman who volunteered for it, and hopefully we're able to make it happen. It's a big challenge, obviously. Nothing's guaranteed. A lot of things can go wrong. But we'll explain what can go wrong, but we'll take a shot at it today.
Did you make sure the moon's in the right place?
Well, good question, actually. The moon is not always positioned appropriately, when we want. Like today is like noon. The question was, for me, is the moon located properly in the sky? If it's too low, we can't do it. Obviously, the antenna, is going to go through the houses. It may not be there because sometimes the moon is just visible at night. And so the location of the moon and the moon window with Europe had to be calculated. So today was actually the perfect day for this day. It just happened this way. We have a nice moon window. The moon is rising right now here, and it's about to set in Europe, or it's on its way down to set in Europe. So we have a moon window with Europe right now. And so we'll take advantage of that, and hopefully we can make it happen. So this is a bit of a representation of what we're going to try to accomplish today. So we are going to transmit radio wave with a power of 150,000 watts of effective radiated power. It's a lot of power. And we're going to, obviously, these antennas, going to see in the pictures, act like as a laser beam, literally, right? They really focus all this radio wave into a very narrow beam, and obviously it has to be directed at the moon pretty precisely. There's not much margin of error to it. So the antenna, as we're going to show in a few slides, are built this way. The whole system is built this way. So we're going to target the moon, and once the radio or Yo, who's in the Netherlands, transmit back to us, hopefully we can see it and hear it, that's going to be received by my station at home. And we are going also, we have installed viewpoint and on a surface probe in front of the radio station. So we're going to capture the audio also coming out of the radio, which we'll route in here. And we're going to try using the decoder, the same decoder that I'm using at my radio station. We're going to run both in parallel. We're going to try to decode the message coming in, essentially coming through the viewpoint. So we'll test that technology. A few key facts here we need to point out. The round trip go to move back and forth is about 500,000 miles. Tremendous distance. It's 250 dB of attenuation. It's a very long distance, obviously. The moon itself is a very poor reflector. The moon reflects roughly only 7% of the energy that you hit it with. The poor reflector, it's not a good reflector. It's very small in the sky as well. So what we're getting back, the signal coming back from the moon, the audio signal, is going to be so weak that most likely we will not be able to hear it with you all here. It's buried in the background noise. But the computer is capable of better than all here. The computer is going to be able to pick it up and it's going to show that signal like on a waterfall. Like, you know, a radar echo, if you will. Echo radar, you know, they transmit, when they get back, they see on that big screen the white dots, right? So we're going to have an echo radar, if you will, trace on the waterfall that we're going to be able to see as a representation of the signal. We don't have time to go in detail, but there are many phenomena that makes this whole process very challenging. We got some galactic noise. So it happens that the Milky Way is just behind the moon. That noise may be sufficient to bury the signal. Right? So that's what we call a degrade conditions. The conditions can be highly degraded by the galactic noise. If the sun happens to be close to the moon, problem too. There's all kind of other phenomena. You can imagine on the moon there are craters, right? And so the distance when we hit the moon with this radio wave, what's reflected back, there's interference, constructive, destructive interference. So the signal is going up and down all the time. Sometimes fades and disappears completely. The big challenges. Yes.
What's Faraday rotation?
Faraday rotation is, you know, for those who may be familiar with radio wave can be polarized, horizontally polarized or vertically polarized. They can be circular. But when, let's say, we transmit with a polarization horizontally polarized, for instance, as the signal passes through the Earth magnetic field, the polarity is going to be flipped randomly. So if you have a station transmitting on the other side horizontally, and you try to receive the signal with vertical antenna, vertically polarized, you will not hear anything. You have to have a polarity match. So Faraday makes it challenging because it's into polarity. So unless the person on the other side station has a capability to adjust polarity, it may take a while before it can hear you. And that rotation changes over time. It just keeps going like a clock. We'll go to the next slides. Just very briefly, Moonbounce was developed during the period of the Second World War. You can imagine at the time there was no satellite, no internet, no nothing. So how do you communicate overseas on the other side of the world reliably without having this uplink, downlink capability? So the military and other agencies developed this technique in the 40s, literally. Tremendous amount of power, and this was kept secret only for many years, as you can imagine, because this was used, you know, by the military. And so that's how it all started. I must say, before the avenue of the computer, which increased the sensitivity, obviously, of what we can hear, this signal had to be audible, what you hear. And typically, this communication were done through Morse code, this type of communication. But again, the signal had to be audible. So the challenge at the time was higher because there was no computer around. Nowadays, the computer, we don't need to be able to hear the signal anymore. It doesn't need to be audible. You know, to a certain degree, the computer can pick up a signal that's 1,000 times weaker than the background noise. It's incredible. We have actually, I put some samples here of actual sound level, just you can acclimatize your ear with it. So here is what a signal equal to the background noise sounds like. Okay, so I'm going to play it. It's the first one to the left here. There's like tone in the background. This is the signal. This is the signal we're going to receive and send. Again, just to give an idea, the intensity of that signal is equal to the background noise. 0 is equal to the background noise, okay? Easy to hear. Now, let's make it a bit more challenging. We'll go 10 times weaker than the background noise this time. Right? But it's getting harder. It's really getting harder. Minus 15 dB, which is equals to 31 times weaker than that background noise, is pretty much the limit of what the human ear can really detect. So listen to this one, and you're not going to be sure if it's your brain playing tricks on you. So here it is. Here, it's getting borderline. This is considered an extremely strong signal when you do Moonbounce communication. Rarely you hear that. It's only a very large station. We'll make it a little bit more difficult. Let's go with 100 times weaker than the background noise. We're not sure, right? The brain is playing tricks on us. We hear stuff. Let me try something. Let's try this one here. Can you hear this one? Can you hear something?
As well as I can hear the other one.
This is a blank. There's no signal on it. So if you hear something, okay, so again, typically the strong signals, when we do this, are in the minus 20 dB range, that is 100 times weaker than the background noise. That's considered a pretty strong signal. So we'll go probably to that level, maybe weaker, depending on the conditions. I'm not sure why. Oh, here we go. Okay, here we go. I'm checking the time because obviously, yeah, we're time limit. So the hardware. So this is a couple of pictures showing how the setup is at my home. So we see the Surface Pro viewpoint sitting right there in front of the speaker. It's raw, right? It's picking up the audio directly through the speaker. And it's sending the audio obviously here. Chase is set up. And what we see here, we flip the camera so we can see the radio frequency, and that's what we see here, right? So that's the viewpoint essentially facing the radio. So when we transmit, we're going to see this whole thing going live. The antenna itself, I spent 3 years. I spent 3 years developing this system. It's a very large. Each of these antennae is about 40 foot long. So it's longer than I'm not sure how long this thing is here, but it's very, very large. It's as big as a small house. Yes?
Is this in Carolina?
It's natural.
Oh, good try.
So it's as big as a small house, it's huge, and the challenge with this in terms of the engineering behind this is that we need to be able to move this to the degree precise, like the laser beam starts to hit the moon. So the challenge with this system is is not insignificant. So there's a rotator here, for the azimuthal positions. There's a rotator here for the elevation. And when I developed this antenna years ago, one of the challenges I explained earlier in Moonbounce is that the polarity flips with the Faraday, right, as the signal goes through the Earth magnetic field. And it's a challenge. It's one of the main challenges in Moonbounce communication. So what I worked on and developed is a system where I rear-mounted this monster antenna and installed a rotator in the back here to be able to rotate, to adjust the polarity at will. So this is the antenna. I call it TARP, which stands for Triangular Array Rotatable Polarity, right? The polarity is rotatable. Again, 150,000 watts. Sometimes when I transmit, the lights literally flickers in my home, and weird things happens. Fan starts spinning. Yes, I do have a license. I have a license from the FCC. You need a license to operate on frequencies and things like that. It's VHF. It's 144 megahertz. Right, see the frequency?
Okay.
Yep.
We're using this antennas for except for cool moon bouncing.
I'm sorry?
What are you using these antennas for except for cool moon bouncing?
These are mainly designed for moon bouncing. They're tuned to very specific frequency range, very sensitive. I can hear satellite passing by. We do satellite communication as well. The satellites that are equipped with transponders and repeaters, so when they fly above, with your software to track them, you can literally use the satellite to relay your transmissions. The frequency, uplink and uplink, downlink and uplink you can use. You can do that. Yeah.
So you may have mentioned, but how is this all funded? It's personally funded?
It's personally funded.
Wow.
It's expensive equipment.
That's what his wife has told him.
Well, what are your energy bills like?
Let me point out the 150,000 watt, how it works. There's 150,000 watt of effective isotropic radiated power. So what that means is that what we're actually feeding in the antenna system is 1.5 kilowatts. But the antenna acts as an amplifier, if you will, concentrate, focuses all this energy in the beam, just like when you have this laser pointer, this principle. So the equivalent power being radiated is equivalent to having a radio station, right, regular FM radio station, transmitting 150,000 watts. That's the equivalent of that.
But it consumes the same amount as a Vitamix blender.
Right, as a hair dryer, if you will. Yeah. Just briefly, software we're going to use to decode this. There are not that many, obviously, software to this, but there's a gentleman who actually was Nobel Prize in Physics laureate for his discovery in the pulsar areas. And anyway, he does a lot of programming and developed the suites of programs, software, to be able to do this kind of communication. Joe Taylor is very well known, and happened to have some communication with him as well. So this is the software we're going to use. We could talk a lot about this space communication. There's also communication mode where you can also bounce radio wave off meteors entering the atmosphere. Right? When there's a meteor entering the atmosphere, it creates plasma trail. And during that tenth of a second or second, sufficient to bounce radio wave and make two-way communications. That's another mode. So there's all kinds of things going on right now. Very interesting. Digital mode communication opened the door to so many interesting things to do. Just briefly about the antenna. So this is the most important part of piece of hardware you set up. Obviously, everything is important because when you cannot even hear the signal, any flaw in your system may be fatal. But the antenna system is particularly critical. So on 2013, this is my first build. At the time, when I heard about Moonbounce in 2013, I had never heard about it, and I found it really cool. I said, there's no way in the world that I'm not going to try this. I'm going to try this. So I started building antennas. I have been building antennas all my life, but these antennas are different, right? They have to be configured in a very different way. So I started working on building stuff, and 3 years later, I had finalized TARP, this triangular antenna system, which is giant. At some point, I had an antenna on the roof, and I was spending dozens of hours on the roof, and some people didn't like it. So even at night, when there was a boy, I was just standing on the roof at night to fix that. So that was not safe, right? So I moved everything in the backyard, and I was fortunate enough that it ended up on the magazine in 2016, at the end of 2016. Briefly, just to explain, when we build this kind of antenna and all the engineering around it, the antenna has to be built precisely to the 16th of an inch, literally everything. Yes, we use software like a CAD software, where you model the whole thing, right, all the distance and everything, and then you see the resulting radiation pattern that emerges out of the model. So this is the radiation pattern emerging from TAR, the antenna system. So we see there's a beam to the left, it's like kind of laser beam, it's very focused. And the thing that's really even more critical is around here, there's nothing, right? So it rejects, the antenna rejects all the surrounding noise and really just focus what's ahead. It's really important to reject all this noise around. You can imagine that in a neighborhood, for instance, the neighbor may be using junk electronic that emits tremendous amount of electromagnetic noise. Somebody, drying their hair. There's all kind of stuff happening in the neighborhoods. The city itself has a huge background noise, and as we move along, right, we know there's more and more electronic, more cell, more 5Gs. The electromagnetic pollution is very significant. Yes.
I know for astrophotography, it's easier when you get out of a city. You can reduce the amount of light pollution. Is it the same where you
Absolutely.
But I'm assuming taking your antenna out
Absolutely.
much more.
Absolutely. You can go in the wild somewhere. You're good. You're good. And then we see also, when the antenna is elevated. Currently, the antenna is elevated at 48 degrees. The moon is going to pass close to that point, and so we see that it's not picking up anything from the ground level. Right? Really important to reject all the stuff at ground level. Obviously, it's not perfect. And there's white noise, there's all kind of source that you can't avoid. And that's going to be a main challenge to me, right? The noise. Is the noise level sufficiently low to enable a two-way communication, right? With signal that we cannot hear. It's a huge challenge. Just some engineering that went behind the construction. This is just an example. The polarity control, right? When we turn this antenna, I have a video. I'll show you the video of how the antenna rotates. This is the polarity controller that was developed. I worked with a very good systems engineer. Bill was his name. November Delta Zero Bravo. So I worked with him and put this control box PLC and developed the application specifically for this, to be able to control this rotation. So there's all kind of features that is embedded in this. I'm not going to go through this, but there's a lot of effort that went into this. This is how things get bad. So there are people doing this that are much crazier than I am. This is an example of what we call a super station. You see these chassis here just to be able to move this monster. So there are 24 giant antennas here. It's Gary KBRQ. It's huge. And when you get to that level, right, the radiation pattern is even more compressed, like a laser beam, really thin. So you need to be able to move this monster by a degree or 2 degrees, right? It's that precise. So, and even worse than that. There's 48 monster antennas, big W5 UN. It's incredible, and you can imagine the maintenance on this is not easy, because if you just need some moisture getting in one of the cable, right, that shorts connection, the whole thing is not going to work, and you need to find where the problem is, right? Imagine where the problem is there.
With an antenna your size, are you aiming for a particular spot on the moon, or just the moon in general?
Just the moon. The beam is not sharp enough to, to have a specific location on the moon. When you increase Sometimes you may get to, or if you have a dish, parabolic dish, to a certain frequency, then you can really target a specific point.
How much
Yes.
is that being diverged by the time it is?
And this one's going to go pretty wide. Really wide. Last question, and then we'll move to the demo. Yes, go ahead.
Well, you just mentioned a dish. Why not a dish? Why are these not dishes?
Yeah, it's all about frequency. At this frequency, 144 megahertz or VHF, the wavelength is still too long, and the dish will not do a good job. You will need a huge dish, maybe 50 foot in diameter or something really big. But when you get in the gigahertz, like 1.2 gigahertz, the sound frequency, the 5G, for instance, 2.4 gigahertz, this is all dish, right? That's where you have to move from these, what we call the Yagi antenna to the dish antenna. When you get to that gigahertz, is the threshold where you have to switch to different antenna configuration. Okay, so it is, let me see here, 128, we're getting close. So what we're going to see, we're not going to be able to hear the signal most likely, as we saw, right? But we're going to, the software is going to turn this inaudible signal into a visual trace that we can see. When we do the demo, what we will see or hope to see is trace like this, right? When we see a trace like this, it is you on the other side of the world, that's him talking to us. So we're going to have to point this little green pin here, the decoder, above that trace and try to decode. So that's what we're going to see. Once we start the demo, I will become more quiet because I'm going to need to focus on the setup, because this thing just doesn't happen by itself. There's adjustments. We need to adjust the polarity, right? We have a match polarity. There's some adjustments, so I'll become a bit more quiet. But we'll try to make it happen. I want you, before we keep going, a video of the antenna and how it rotates and everything. I put some cool music over it.
What kind of antenna is your cohort on the other side have?
I will show you right now. So brief explanation. So this is the antenna of a friend on the other side of the world, Yoke, and his equipment. What is that? Yoke is actually a legend. I need to point this out. He's a pioneer legend in the field. I do have maybe something cool I want to show here. I'm not sure why I don't see black here.
Jimmy, do you know what his dog's name is?
He has a few dogs, so I don't recall. So, Yoke is a pioneer. If you see the date here, 1973, we had the first Morse code communication with the Naval Research Lab, Washington, D.C., 1973. I was not born. And he was doing this stuff and building his own equipment. So, we're not dealing with an amateur, we're dealing with a pioneer in the field. And I had my first contact, Moonbounce contact with him in the beginning. So he was kind enough to volunteer for this. Briefly, the protocol. So when we do Moonbounce, typically, when the signal is strong enough, you can do free text. You can. The signal are not strong enough, you can do free text, but it's going to take longer, right? But typically, to have a straightforward contact, we follow a protocol. This is an example of what you will see. So when we hopefully able to see the signal, we're going to see you calling us, right? Us, well, KK65H, this is my license, FCC license. He's going to call us by my license name, followed by his license name. We're going to reply to him with his name, my name, and OO. He's going to reply with OO with the received, right? It's an acknowledgement and received, and we're going to reply with RR. 73, it's a code for goodbye or thank you. But we're going to attempt, if the signal is strong enough, we're going to attempt some free text. See if we can get the free text from it. Each sequence lasts 1 minute. Okay, so what I mean by that, since we cannot hear anything, so we have a protocol where during 1 minute, he is going to transmit. The following minutes, I am going to transmit, if I can see the signal, and so forth. It's structured this way. Since he is in Europe, he's going to be transmitting on the even minutes, and we're going to be transmitting on the odd minutes. That's the protocol pre-established with all the Moonbounce servers. It's not only today, that's a typical protocol. Okay, so we're going to switch to now the log me in to the remote station. And you see a little trace here, and that's probably him. We see other station here to the left. See, these are call sign from other station, RX1AS, a station from Russia. So we're picking up signal from the moon right now. OK1 VRY is from Finland. And the signal, the trace we're seeing here is probably our friend Yo, because that is the frequency we agreed upon. Are you able to position yourself, Chase, to that just above 0? And I'm going to rotate a little bit the polarity of the antenna to see if we can maximize the signal strength. You see now we're 90 degrees, so our antennas are vertically polarized. We're going to turn that a little bit, try to fine tune. We can fine tune the signal a little bit.
So was the polarity like on your antenna changing? You did that?
Yes, when I move this way, the antenna is literally the polarity is changing. So we're going to give it one more sequence. You see, Yo is telling us we're clearly picking up the signal. Minus 25 dB, right? So at minus 20, that's 100 times weaker than background noise. Minus 25, it's like 600 times weaker than background noise. We can't hear it. We can see it. That's a cool thing. So we're going to give it one more sequence, try to fine tune the signal.
The quieting you hear is our software or audio video technology muting the background noise a little bit.
Yeah, so that was a big thing that I wasn't sure. When we installed the viewpoint and Surface Pro, the first question was, is there any kind of processing of that audio? Because if you have noise canceling capability and all the stuff, it may wipe out, wipe out, right? So we were not sure what kind of audio we would get because of the processing. It's nothing better to just have raw audio, no processing at all. Okay, so now we're fine tuning a little bit. The signal is pretty good. Pretty good. And so we are going to we're going to reply to him at the next sequence. So when I click on this auto is this button here. We're going to be transmitted. So we hear the fan, there's a ton of amplifiers and fans. Actually, Viewpoint does a good job at quieting everything down. So the transmission lasts about a minute, up until 30 minutes and 48 seconds. It's 48 seconds of transmission exactly. There's 12 seconds of dead time to allow the software to decode and all this stuff, right? And then the next sequence, the other person transmits.
Is it repeat the transmission or is it just one?
It's one. Now transmitting right now. That message. This.
Is that message sent in one stream?
Yes.
Or is
Go straight bounce to the room. Do we hear something? Yeah, good. So what we see here now is replying clearly. The trace is pretty clear, pretty clean. Did we decode something here? Yeah, that's good. So we got it. So with the Viewpoint Surface Pro, the speaker, we're picking it up as well. It's decoded. So he should be transmitting RO as a shortcut for receiving. And I'm going to be transmitting RRR to acknowledge that. And as we can see to the left screen, there's other stations that we're picking up from the loop. It's getting busy, actually.
When you were adjusting the antenna, what are you looking at to see if it got better or worse?
We rotated the
I'm asking that, when you're hitting the button on the screen, are you looking at something, one of these lines or numbers, see if it's getting better or worse?
I'm not sure if I understand the question. When I click here, you mean?
No, when you were adjusting antenna 1.
Oh, okay, this is the polarity. This is the polarity.
Right, I understand what you know better or worse. How do you know if you're making?
Oh, yeah. You need to take a sequence. It takes at least a sequence to see if the signal is going to get better or worse.
Right, but what are you looking at?
Oh, the trace. The trace. The intensity of that trace
Got it.
on the waterfall down. That trace is all we got, right? I'm sorry, there's a lot of noise I cannot hear you. We'll take the question at the end if you don't mind. You see, there's something that's going on the left side here. There was a lot of noise. And now the noise stops. So there may be something in the neighborhood. You see here this white thing going on. It was a very noisy moment. A few seconds of extreme noise. That probably wiped out a signal for a little bit. So we're going to keep transmitting RRR. So what Yoke attempted to do in this sequence was to send a free text. That's what we agreed. So we see we decoded something here, but not strong enough. It's not at that kind of 20 dB threshold to be able to decode the free text. So it's going to be challenging. We'll try a few sequences. The software has an averaging capability, so it just compiles the sequences, overlay them, and then if there's a decode behind it, it's going to show you the decode. So we'll give it a couple more sequences. So it is a hobby that you can spend really many hours doing this, because a contact, the longest communication that I had took 3 hours of fighting, making it happen. So you can fight in the noise and conditions for quite some time. And you see, signal is pretty good. Again, very clear. Everybody sees it. You see the trace here?
Where is the frequency trace on?
So we'll see if we can decode his message. We see another radio station here. If you look here on that frequency, you see that trace here? See how? These are other stations actually communicating.
How do you prevent the stations from colliding?
Like, so to be overlapping?
Yeah.
Sometimes that happens. There's enough frequencies that can be chosen, and the bandwidth, right, is pretty wide, so the chance that you're going to be at the same place are not very high, but it happens actually. Especially if there's some people going on islands, literally, that's getting set up on islands and doing Moonbounce for a week, and obviously all the stations all over the world are highly interested in making that contact, so we end up with dozens of stations trying to communicate with them. Yeah. So you see the signal is not sure if it's going to be strong enough for a free text. We will give it one or more to sequence. Viewpoint and Surface Pro, we decoded everything so far. Everything. Are we seeing the signal? Oh, yes.
Is that where you want the trace?
It's at 0.
I
So
had it, just
no,
zero.
it's not this one. It's right here. So we're not decoding every time. We see here, but it's maybe 2 weeks today for free text. So we'll see. We'll give it one more sequence, and then we will transmit the thank you.
Is it possible that he can receive us even if we can't receive him?
Yes.
So
And
can
that's
can
one of
we
the
try
challenges.
sending him something?
Yeah, we will do that. We will do that. So we will send in a thank you, The signal is increasing in strength, as we can see. The trace is becoming more white. Stronger the trace, the signal, the trace is going to become more obvious, more kind of white. So let's look at the decodes. Here we go. We got it. In touch help. So we're sending him a thank you. So I am communicating with Yoke on the side just to let him know what's going on. He's as interested as we are. It's the outcome of this, but it worked out. Were you able to decode this one?
Yeah.
You decoded it too?
Yeah.
So on a Viewpoint Surface Pro, incredibly, this microphone and going through all this processing, coming here, we decoded it as well. Take a screenshot. Yes.
So this signal that started at 400 and is going down, is this somebody just changing the dial?
Oh, there's sometimes a plane may pass by and you get an echo from the plane. You can bounce off planes as well.
But is this frequency that we're seeing on the
Yeah, this is
x-axis?
frequency access, that's right.
And so why is the frequency seems
The
to
Doppler
change?
effect. The Doppler effect.
Ah,
When your train passes, you hear,
brilliant.
that's exact same. That's how the radar works. This is a radar system, right? We're bouncing stuff, we're getting a return, it's put on the waterfall, it's identical to any radar principle.
Wow.
Actually, there's a frequency I could tune in where we detect a radar from France, a military radar that transmits a million watts of pulse to try to locate all the satellites in space and planes.
Wow.
And we detect it very easily. It's called Grave radar.
Are these characters ASCII? Is that what's, or is it like UTF-8?
Oh,
Can you
great.
send emojis?
All right, so we got it. Okay, you got it as well. You got the. I'm going to send it to him if you don't mind, because I think it's very nice for him to see that. There you go. And we'll send it right now. Thank you. He's sending a last text apparently.
I know.
So this is
I see it.
you need a strong signal. You see at minus 20 dB level, 100 times weaker than background noise is getting where it needs to be to do free text. We can free text is great. But you need a certain signal strength obviously to be able to do that. Happens that you also is transmitting with also 100 to 150,000 watt of power to the station. We build those little amplifiers and everything. So I will let him know that we are done. Let's see if we get this one. Did we get the second one on the Surface Pro? Excellent. So the in-touch AV technology is being tested to its extreme degree. All right, so we didn't get the last sequence. Probably will take a few more, right, to get the average, but you get the point. So I will go back to the presentation. Okay, do you want to turn off the sound, Chase? So, that was the last slide actually. So, any more questions? I'm not sure how much time we have. I mean, just well, 10 minutes. Yes.
In terms of software use, is like can you radio or is there like some source programs that you use to assemble all of stuff?
Repeat your first time.
What kind of software do you use to build that?
The antenna?
No, the software that you use.
So the decoding is this Joe Taylor, as we saw, who created the software. So I didn't do anything. It's a gentleman who created the software.
Yeah, it's basically just a software defined radio that takes up the whole thing.
Yeah, I mean, I didn't go through all the hardware. There's a ton of hardware in the system. For instance, we go back to the antenna system. We saw the polarity controller. You see there's a box here. We don't see it really well, but plastic box. So there's a lot of electronics because the signal, as soon as the signal comes out of the antenna, you don't want that signal to be attenuated, through the cable and all that. So there's a low noise preamplifier set up on top of the tower to immediately amplify a signal before we use it. Very important. So, and there's a sequencer system. Obviously, when we transmit the signal, we cannot be transmitting through this low noise amplifier. We're going to blow it up. All right, so there's literally two tracks. There's a transmitting track and a receiving track, two different cables with relays. So when we transmit, the low noise amplifier is bypassed, and the power goes straight to the antenna. When we're on the receiving mode, the relay goes into a receiving, and then the low noise amplifier is in line. So there's a lot of sequence going on, and to make sure that you're not transmitting or there's not a spike, during the relay switch, there's also the little box here that we see that induce a delay of a few millisecond delay to make sure you don't want to blow up your preamplifier. Go ahead.
By Lunar Jimmy.
Oh, we got it? Let's go back to the... Here we go. So we got the last... we got the last one as well.
What's the character limit on those?
13. It's less than Twitter. There are different modes, right? This software has, has different mode of, if you look here, we're using the JT65B. There are many different modes used for different applications. Actually, since we have time, let's try to do a cool experiment. So we're going to try to hear our own echo. We're going to transmit a tone of 2 seconds towards the moon, and then stop transmission. We're going to be listening. The radio wave takes 2.5 seconds at the speed of light to hit the moon and come back. So we may be able to see, we should be able to see our own echo trace, right? Now, here's the challenge, and that I don't know. When the radio wave again passes through the Earth magnetic field, it's going to spin the polarity. So we may be transmitting horizontal and receiving vertical. If that's the case, we're not going to hear our echo. So hopefully that Faraday rotation effect is not going to kill us, right? So let's try it. We will go into, and I'm going to take a picture of that. Just have the record. Give me a second. So we have 5 minutes. We have time to do this. There we go. So we're going to switch into the echo mode. And here we go. So we are going to transmit now and see if we can do this a little bit. Here we go. So here we go. We're transmitting right now. So we're transmitting in 2 seconds, and then we listen for 2 seconds. Yeah, we're getting a signal. Let's wait a few sequences. You see that peak here? That's our echo. Very clearly sticking out of the binoculars. And we can see the trace. You see, look here on the graph. Look here. You see the little white dots? We give it a few seconds to have more of them, but that's our own echo radar. The same principle as a radar, right? When a car right targets you with the device, hits the car, echo comes back, it's the same principle. So we're representing it in the form of waterfall trace again, but we can clearly see our own echo here. And what's interesting, we see the signal is very variable because because one time we get a white dot, the other time not, right? It shows how much the signal is going up and down all the time, going through these craters, you know, in the moon. So we probably can stop here, but we see the trace. There you go. So I think this set of presentation, so we were able to decode everything using the surface flow and viewpoint, even the free text. I am impressed myself because we weren't sure how this whole thing would go, right? Many things can go wrong. When I got up this morning, I turned the equipment on and I really wanted to make sure I don't forget to turn one of the switches, the many switches to turn on, and then there was no signal. So I said, holy cow, there's no signal. What's going on, right? The preamp is blown up, you know, this whole thing goes up in flame. So I went to check under the tower, and yesterday I had recharged the battery. I use a car battery, so there's no noise. I don't use power supply or anything like that, minimum. So I use a car battery, and I had recharged it yesterday evening, and when I removed the flame, the pole just popped out, and that's why it wasn't. So it was an easy fix.
If you ever want to test something, try it in front of a room full of people. The perfect test.
Yeah, it's a lot of prep. There's a lot. This setup actually was more time consuming. The device setup is already set up, right? So it's just a matter to make it work. But this setup with the viewpoint, clearly there was audio tampering happening. There's audio processing. We're not sure how this will go. It's going through microphone, the raw mic, right? We saw the picture, the raw mic from the Surface Pro, so we're not quite sure how this will behave. And amazingly, we're able to decode everything, including the free text. So I'm pretty impressed by that. Yes?
Did you start off, before you got into this, doing any amateur account or anything?
Yeah. Since I'm 12 years old, I've been building antenna. But what's nice, I've never been really a talker. I don't talk, but I like the digital, I like Morse code and stuff like that. But nowadays with the digital communication, so much cool stuff you can do, and you can challenge yourself, from an engineering standpoint. Involve software, hardware, integration of both, right? That's a bit what we do here, right? We have hardware and software integrated, the same stuff, right? Playing with rotators and yes.
The modulation seems very basic, like considering all their visual modulations and how they have it is. Is there some limitation on what you're allowed to use as an amateur radio operator for like modulation?
Not really, as long as your bandwidth is, you're operating on a frequency that you're allowed to, the band, you're not emitting noise and crap, because at this power, also you can imagine if your equipment is not optimal, you can create a lot of interference in the neighborhood. There's a lot of things that can go wrong, but if you stay within the
neighborhood being the whole planet, right?
We could say that, yeah, we could say that.
Well, thank you very much, Jimmy. This is fantastic.
Okay.